Welcome back. We're going to continue chapter 3. We're going to talk about another measure of center and spread. We've been talking about center and spread in our last video. We talked about the median, right, as a measure of center. We also talked about the 5-number summary, the interquartile range, the range itself as our measures of spread. So in this video, we're going to look at the mean and something called the variance or the standard deviation. The mean is just another word for an average, and our sample mean, x bar, is equal to the sum, which is what this squiggly kind of Greek letter sigma here represents. It's the sum of all of our individual x values, or just all of our individual data points, divided by n, little n, which is our sample size. And this can be kind of further reduced, right? We can call this 1 over our sample size and multiply this fraction by the entire sum of our values in our data set. So just this note here, the mean or the average is going to be affected by outliers and by strong skewness that we've seen in the past videos. But however, our median is actually more resistant. It's actually not as affected when you do have outliers or skewness. However, the mean does provide more information than the median, because the mean takes every single data point into account, right? Where the median just cares about where the data lies, doesn't care what the actual values are, right? So for this reason, we prefer to use the mean as our measure of center, except when we have outliers or definite skewness. When this happens, we use the median as the measure of center. So this is a really important note. You'll definitely see this on homework and most likely on your test. When you have skewness or outliers, you don't want to use the mean, you want to use the median. And other than that, right, if you don't have skewness or outliers, then you prefer to use the mean, okay? So let's do a quick example here. Let's just say we have a simple data set, right? Let's keep it really simple. Oops. One, 4, 5, and let's just call it, let's say 6. So let's say we have a small sample, right? We have 1, 2, 3, 4 numbers in our data set, right? So this means our n, or our sample size, is equal to 4, right? Because we have 1, 2, 3, 4 numbers. Okay, so we found n, which is great. So now we need to find the sum of our x's. So the sum of our x's is just going to be the sum of our data, right? So we'll take 1 plus 4 plus 5 plus 6. And this, if you add all these together, we'll get 16, right? So now we just take the 16, divide it by the 4. Do this down here. And we can say our sample mean, or our sample average, is just 16 divided by 4, which equals 4. Pretty straightforward. Okay, I'm gonna write down those numbers again just before I forget them. We had 1, 4, 5, and 6, and we already calculated our x bar, which was equal to 4, and we will need that to calculate our variance or our standard deviation. So um, variance and the standard deviation are another measure of spread that we can use. This can tell us how spread out, how far apart, or how close together our data is. And again, just like the average, we'd prefer to use the variance and the standard deviation if there is no skewness, right? Because again, you can see from these formulas, we're adding all these individual x values up. So we're again using all of our data at hand to calculate this as opposed to those quartiles that we've talked about before. So this is the variance is the sum of squared differences. So what this means, the sum of squared differences, is that we're taking a sum, right? We're adding each x value. We're taking the difference actually from the mean, right? So think about this. All we're doing here is seeing how far each of our values is from the average value of all of our values, right? You square each one of those values, and that's basically, you can kind of think of it like making it strictly a positive, right? If the x value of the first value is smaller than our mean, just like was the case, right, in our data set, if we take 1 minus our mean of 4, we'll get a -3, right? But then if we take 6 minus our mean, we get a +2. So if we add +2 and -3 together, that total difference is only 1. Summing it that way kind of makes it seem like on the whole, we're closer to our mean than we really are, right? That 1 is actually 3 spaces away from 4 below it, right? 6 is only 2 spaces. So the total difference there, the total distance, right, from 4 between those two is actually 5 instead of only 1, which is one of the reasons we're squaring this. And then we basically just take the average almost, right, of those differences that are squared, right? Here we divide by n-1 instead of our n, which we saw in the mean. And there's a reason for that, but we won't go into it too far here. So there are 2 different ways to calculate the variance. You'll get the same answer either way. I think it's a little clearer to calculate it this way. You can see this has a couple extra parts to do. So we're going to focus on this method first. So in this first method, all we have to do, I know this looks a little scary, just kind of ignore it for now. All we have to do is take each of our values, just like we did last time, right? And we have to take the difference of our mean, right, which never changes. It's always going to be +4. I don't know why I wrote a negative there. I'm sorry. So we take that difference. So let's do that. So 1 minus 4. This is x1, right, minus our x bar. And this is, let's just throw the squared sign on there. This is -3, right? 1 minus 4 is -3. And then we have that squared up there. So if we square it, what do we get? We get 9, right? So that's one value. If we do this again, now if I take my next number here, right, and do 4 minus 4, right? I'm taking this 4, subtracting it from our average, right, x bar, and I square that. Well, that's 4 minus 4 is 0, right? 0 squared is 0. 0 times 0 is 0. So now let's do 5 minus 4 squared. Well, that's 1 squared, right? 1 squared is 1. And lastly, let's do 6 minus 4, right? I'll do that down here. Sorry for going a little all over the place. 6 minus 4 is 2. 2 squared, or 2 times 2, is just 4. Right? So now, what do we do? Now we need to add each of these numbers together. Uh-oh. I lost it. So we had 9 plus 0 plus 1 plus 4, right? We'll add all of this up and we'll divide it by the sample size minus 1. So 9 plus 0 is still 9, plus 1 is 10, plus 4 will give us 14, and 4 minus 1 is 3. So if we do 14 divided by 3, 14 divided by 3 is equal to, sorry about that, 14 divided by 3 is equal to 4.6. Repeating. So this would be our variance, right? And just as a reminder, I'll write it back out. We got that from the last thing, which disappeared. This was each of the x values minus our sample mean, 9 plus 0 plus 1 plus 4 over 4 minus 1. And we got 14 in the top. 4 minus 1 gave us 3 in the bottom. So that's our variance, okay? So now the standard deviation is basically just the square root of the variance. So the variance is in terms of squared values, which doesn't really always make sense, right? If we're talking about our data is in dollars, right? We have an average of $20 spent at the grocery store, and we calculate a variance, right, for the number of dollars spent at a grocery store. Talking about dollars squared or squared dollars doesn't really make sense, right? So most of the times we're going to take the square root of our variance to calculate the standard deviation, right? Just to kind of get our units of measure to make sense. So example, dollars squared, right, doesn't make sense. Miles per gallon squared, etc. But if we take the square root, that's squared, dollar squared just goes back into dollars, miles per gallon squared just goes back into miles per gallon, and so on. So if our variance was 4.6 repeating, right, we'll just take the square root of that. And so if we take the square root of that, I get square root of 4.6 repeating is 2.16. And that would be our standard deviation, which we could just write as this little s, right? Instead of s squared for our variance, just call it s. Okay, and that is the mean and the standard deviation.